Hello everyone, my name is Mohit Deshpande, and in this video I want to discuss some steps that we can do to monitor how our network is actually learning. And so there's like two different things that we want to plot here. We want to plot the loss and we want to plot the accuracy, and we want to plot the accuracy or the loss on the training set as well as the validation set. And so we'll be discussing all this stuff as well. And one little thing that I want to mention here is with learning rates. So this is actually taken from a Stanford class, CS231N, and so I kind of took this chart, borrowed this chart from there. So I just want to take a second to explain this, because learning rate is an incredibly important parameter, and a lot of the parameter update algorithms that have been coming out in the past few years have been trying to, all about adjusting this learning rate, because it's an incredibly important parameter. And you can see from this chart kind of the result of having good learning rates and having bad learning rates. Your loss can tend to just spike up, and it's not going to be too good. So the analogy that I want you guys to think of when we're discussing learning rates is, imagine that you have imagine like you're on a ball rolling down like a bowl or a cup or something, and so there's like an absolute bottom to the to the bowl or the cup, and you're on a ball and you're just kind of like traversing down this. Another analogy that people like to use is, suppose that you're somewhere on a mountain, you're blindfolded, and you're trying to get down to the valley, to the lowest point. And so you take like little steps, right? That's kind of how that how gradient descent and the parameter update stuff works. And the size of the step is the learning rate. It's also called, which is why it's also called step size. And so this, again, it's a really important parameter to select. And so how do you know that you have a pretty okay learning rate, or at least maybe an initial learning rate if you're using an algorithm that changes the learning rate? How do you know that it's working is by looking at the loss curves. So everything here is nice and color coded. So I'll kind of like try to compare these learning rate analogies with the act of like a ball rolling down a hill into a valley. So let's discuss what happens when you have a low learning rate. So that's by that blue line there. So if you have a low learning rate, notice how that curve it's going. I mean, loss is slowly going down, and the key to this is it's going down quite slowly. And so what happens when you have a low learning rate is that you will probably hit a really nice low loss value. The only issue is that it's going to take you quite a long time to get there, and so that's not really a good thing to do, because especially if you're running on your own GPU, or you have something like a Google Cloud Compute instance, or an AWS, or whatever service you want to use for GPUs, if you have that running, then time is money, and so you don't want to sit around waiting like months for your network to converge, all because you have a really low learning rate. And so these are the kind of things that you can always plot loss and infer a lot of things about it. So that's kind of what happens when you have a low learning rate. And so let's kind of jump to the other side and discuss if you have a very large learning rate. Or actually, before we do that, let me make that analogy. So it would be like, again, go to that analogy back to where you're blindfolded and you are on you're on some mountain, you're trying to get down to the valley. Well, having a very low learning rate means you have a very small step size. So you're just taking like little tiny baby steps based on just kind of you feeling around where's around you. And so if you do this, right, you're going to be taking really small baby steps the whole way. And that's going to be kind of, you'll eventually get there, but it's going to take you quite a while. So the lower learning rate is not too great. So okay, so now let's discuss, you have high learning rates and very high learning rates. So you notice actually for the very high learning rate is your loss actually goes up after some time. And the reason for that is because you're taking huge step sizes and you're overshooting is basically what's happening, right? So again, if you're like, if you're maybe like, now let's use the other analogy. If you're on like a ball rolling down a hill, taking a very large step size means you just overshot the low loss value, and you're actually like, if it's very very large, you're like end up with a higher loss value than when you started, right? So like think of the shape of a bowl. If you're kind of like towards the bottom and you take a very large step in one direction, you might end up actually at a higher loss value than where you started. And so that's kind of the consequences of having a very high learning rate. Now, if you have a high learning rate, you might look at this and say, oh, well, this is like okay-ish. I mean, it's going down quite quickly, but the issue is that it's converting to a still a high loss value. So what this equates to in the analogy is that you're like just bouncing back and forth on either side of a loss value, right? So again, think of like a parabola or like a bowl, a bowl shape. You know, you're just jumping on either side of the smaller loss value, and so this is why high learning rates aren't quite that good. And this is kind of what the graph looks like of having a high learning rate. And then so you want something that's kind of in the middle. You want in the red, that's that good quote. That's probably being quotes actually. You want a good learning rate, one that will, it's going down. It's not going down too slowly, but it's also not converging to a high loss value. So if you're ever having issues with your network training, maybe take a second, go back to the slide and look at these loss curves. And maybe also what you want to do is build like a really small network and try messing around with these learning rates. See if you can reproduce these graphs. So try giving using just gradient descent with a huge step size or learning rate, and try doing it with a very small step size learning rate, and see if you can kind of reproduce these charts. Anyway, that is enough about learning rates. Let's talk a little bit about overfitting. So this whole problem of overfitting, I mean, we could discuss this for days, really. But and I'm going to show you like accuracy curves in the next charts about this, so you have what you can use to kind of detect this. So overfitting is basically when the model that you're working with doesn't generalize well. What it means is that you're focusing way too much on the training set, and so when you get to the test set, when you get to data that you've never seen before, the model has real issues with this. So that's why we look at training error and validation error, so we can use this to kind of determine if our network is overfitting or not. So what is going to end up happening is your training error is going to be really small because your network's getting really, really good at looking at just your training data. The issue is when it has data that's never seen before, which is in the validation, which in your validation set, which by the way, either is just going to be, when you batch your data, you're either going to have a dedicated validation set for the entire duration of training, or maybe for each epoch you change out which is the validation set. In either case, you end up with a large validation error because, again, it's data that your network hasn't seen before, and so it's focusing way too much on on your training error. And a little bit about why this is usually because you have a lot of parameters and you have a very small training set. And so what happens is your parameters are going to learn the tiniest bit of intricacies in your intricacies in your data. Right? So imagine, I'm gonna have an image of this actually in the next or maybe the slide after that will show you a little bit about what it means to do what overfitting means and whatnot. So I'll have like a pictorial example in just a second, but you have a lot of parameters, a small training set, and so all of the parameters are going to try to learn the very tiny intricacies of your data, and that's really not a good thing because you want your model to generalize well. This is kind of like a trade-off, basically, where you want your model to learn things about the training set, but you don't want it to learn the very tiny details about your training set because you still want it to generalize well. And this is a huge problem. Okay, so a lot of researchers are working on this, and this is something that you need to be very aware of when you're training your own networks on maybe even your own data or even data that's like publicly available data sets. Something that you really have to be aware of is overfitting. But because, fortunately though, this is kind of like thing is because this is such a big problem, there's been a lot of techniques invented to help combat this. So there's early stopping. We'll be discussing that soon. There's regularization that we can discuss. There is one probably the easiest thing to do is just get a larger training set. If you have a very large network, to fit all these parameters, you need a lot of data. And so one simplest solution, again, is just to collect more data if you can. Or maybe use dataset augmentation, right? If it's too expensive to collect new data, you can try using dataset augmentation to kind of help combat combat overfitting. And so there are quite a bit of things that you can, and people are still working on this problem as well. And so there are a lot of different things that you can do with overfitting. And so actually, to make this a bit clearer, and let me show a picture real quick. So here is a little graphic that I made that kind of helps illustrate overfitting just in terms of using a simple graph. So we have these points here, these points, and we want to figure out a good model that represents these points here. So an example of you can kind of see that they actually kind of fall along like a straight line, which is probably the correct fit, correct, maybe that should be in quotes, is probably using a straight line to approximate these points, probably a good idea. But with overfitting, what happens is if you have a a line, by the way, using just a single, a line just has you can kind of consider as having two parameters, right? A y-intercept and a slope, or 2 points. But with overfitting, we have a model with lots of parameters. So maybe this is like a polynomial, and what happens is you're seeing it's getting it's hitting all of the points, and so you can kind of tell this is not a good model to use, right? If you're in between 2 points, when you overfit, you're not going to get a good result. A better fit would be approximating this with a straight line. And in case you're wondering, there is an analogous problem called underfitting, but this is actually not, you don't really run into that problem too often. But right, you see that with overfitting, if this is the training data, you're running into issues where you're learning way too much about the little intricacies and orientations of the training data. And you don't want to do that. You want to have a model that actually generalizes well. And so again, this is a huge problem. And so we kind of discussed a little bit in the previous slide about the different ways that we can help. And we're going to discuss early stopping. But I also wanted to show you, this is taken again from the same CS231N class at Stanford. I also want to show how you can identify whether at least one of the ways that you can identify whether your network is overfitting or not. And that's by looking at the training accuracy, which is the accuracy on your training set, and the validation accuracy. So if there is little overfitting, then your training and your validation accuracy should roughly be they should be kind of close. And what this is saying is that when your network sees things in the validation set which it has never seen before, it still does pretty well. Okay, so that's why it makes sense that this means that there's little overfitting going on when your training accuracy and your validation accuracy are pretty close. Now, if you have overfitting, if overfitting is happening, what's going to happen is your training accuracy is going to be pretty high, but your validation accuracy is not. And so that kind of goes back to the issue of your validation set is something that your network has never seen before. It's supposed to be kind of representative of your test data, which certainly your network's never going to see until the very end. With what happens is your network learns a lot about the training set, and then when you get to the validation set, it just performs poorly. And so this is, by plotting these two things, you can see what's actually going on. And Keras will actually do this for you. You can get TensorBoard working with Keras, and so you kind of use that to see if your network is overfitting or not. And so, speaking of overfitting, one of the things that you can do to prevent this is probably one of the easier things to do besides collecting more training data, is simply by using this technique called early stopping. So early stopping looks again at your training and your validation set accuracies, and basically just says, let's immediately stop training the model right now. when the accuracy in the validation set starts to dip. And so you can see that actually with the training set, and you see that we have this early stopping point when the accuracy of the validation set is starting to kind of fall down. And so then we just say, all right, let's stop training the model at this point, save all the weights, and this is the end. This is the end model. So that's that's early stopping. And to do this in Keras, by the way, super simple, right? You just say you define a callback for early stopping, and then you put that in the list of all the callbacks that you have when you call fit on your model. So there are a couple parameters here that maybe I should explain. The monitor is basically what are you looking at to determine whether you need to stop or not. And so the monitor that we're setting up is actually validation loss, but you could easily set this up to be validation accuracy as well. And then Keras will know like whether you're doing like with accuracy you want it to be max, with loss you want it to be minimized. So Keras will automatically know what you want to do with that. There are two other parameters that come with this. There's a min delta and a patience. And the min delta basically says what's the smallest change in the thing that we're monitoring to consider this to be like an improvement over the previous epoch or not. And so if you set this to 0, that means that, well, if we're discussing loss, validation loss, if the validation loss is lower than it was, this is just lower by any value, then you know that okay, this is considered an improvement. If you set this to something other value, then you're going to look at the difference between the two, and you say, well, this is not like big enough to consider this to be an improvement or not. It usually just sets to 0. For patience, that's how many epochs do you wait before you call it quits. So in this previous chart, maybe this is just saying a patience of 0, meaning as the second that as soon as you measure an epoch that's worse, then you say, okay, I'm stopping right now. If you set this to a higher value, maybe like 2, then you'll say, okay, well, my accuracy is getting worse, but I'll wait another epoch, or I'll wait like 2 more epochs for it to improve. And if it still doesn't improve, then I'll stop. So these are just kind of 2 parameters that we can use. So I'm kind of running out of time here for this video. So that is early stopping, and one of the techniques that we can use to help combat overfitting. But there's another one that we're going to discuss called regularization, which also works really well, and it works kind of in a more direct way regarding the overall loss function and the weights of the network. So just doing a really quick recap here, so I'm running really low on time. We discussed what the different kinds of learning rates, because we're discussing that you should be looking at your training loss and your accuracy to help figure out what your model is actually doing. And so you can kind of look at the different learning rates. We also discussed the problem of overfitting, and I drew this little picture to kind of help make it clear what's actually going on with overfitting. And we discussed a little bit about how you can tell whether something's overfitting by looking at the training and validation accuracy and why these things make sense. And we discussed probably one of the quickest ways to help combat overfitting. It's early stopping, where you just say, okay, as soon as my validation set starts to tank, or as soon as the accuracy on my validation set starts to tank, then we're going to stop immediately. Setting this up in Keras is pretty simple. So that's that's kind of one of the ways to combat overfitting. And in the next video, we're going to be discussing another way called regularization.